Hello and welcome to lecture number 10 of Photo and Non-Photorealistic Rendering. I'm your instructor as always, Leslie Eisted, and in today's lecture we are going to start talking about something called lines and shading. We are going to look at how to draw the contour lines around 3D models, but also try to draw contour lines around objects in images as well. And then we're going to look at various forms of shading these line drawings, so things like hatching and stippling and so on. So just a couple notes. Make sure that you've taken a look at assignment 4, which is posted. And if you have any questions, by all means, reach out on Discord. The other thing I wanted to bring to your attention is that the final project has been posted to Brightspace, and there are a few different components to it that could take some time to render, so please make sure you get a head start. And for the assets that you're looking for, I have not posted them yet. I will try to post them very soon. But I do encourage you to actually reach out to things like TurboSquid to acquire your own assets as well, because you're going to need them. All right. So today we are looking at lines and shading, which is a fun topic. So in our last lecture we focused on toon shading. We wanted to create a cartoon from a 3D model or take a photograph and make it look like it was a cartoon or an animated scene. And that involved quantizing the colors such that you have one or two dark tones for shadow regions, and you have one or two bright tones for highlight regions, and then you have a middle tone for the other regions. It was really about simplifying the colors and sometimes even brightening the colors. And we also noticed that as part of our toon, it actually, while some games have toon shading, like the Wind Waker, without any actual outlines, that's actually not the norm. The norm is for cartoons to have black or darker outlines around the actual objects. And we saw when we used a texture ramp that if you put darkness on the one side of the ramp, it is possible to get kind of a contour-like appearance, but it doesn't really work very well because our UV coordinates for the texture ramp were coming from the lighting incident at that particular surface point, which meant that you only got that dark band in areas that weren't well lit. So it didn't work perfect. Now, if we actually take a look at cartoons, we can actually see a few different things. In simple cartoons, apparently my scroll is not working today. In simple cartoons, like the Looney Tunes, the Bugs Bunny show, you can see pretty much that the line thickness throughout the image is the same. So they don't differentiate between areas of shadow or fine details. Every line is the same thickness. But if you look at other cartoons, like The Lion King, if you actually take a really close look at this, you can actually see that the thickness of the line kind of depends on whether it's in shadow or how it's presenting itself to the viewer. So when we're trying to produce contours for a cartoon, we want to be able to do things like produce constant thickness lines or have the option of having lines which vary in thickness according to their visibility to the viewer. So lots of different ways that these actually present themselves. So how can we actually implement these lines? Well, let's take a look at another style here. So I said that when we're looking at the Lion King ones, you've got the lines, they're sort of being thicker. But to take it to a bigger extreme, if you take a look at cartoons, like actual comic books, you can see that the exterior lines are playing a much larger role in the shading of the objects. So things, as they rotate or face away from you, they get thicker and more visible, the contours. The other thing I want to point out in particular with this comic book slide is that you can see that the contours aren't always just the outer shape of the object. You're also seeing contours where there are creases and folds in the fabric or muscle, and just details of the models themselves. So you're seeing some of the surface features being rendered with these lines as well. It's not just the outer lines. And this is really what we want to be able to recreate, whether it's on an image from like a photograph or whether we're doing this from a 3D model. We want to be able to recreate this look as best as possible. So what I want to do is talk about contours. So when we're looking at contours, we're looking at primarily the outlines of the object. And if we think about it, the position of the contour really depends on the position of the viewer. Contours don't just float in space around the object. We are seeing the contours around the edges of the object as we are viewing it. So the contours live along the outside. Contours, sometimes when we're talking about these, at least in any research, we often include creases and folds and interior lines. And the position of these is also dependent on the position of the viewer. Because if you are not looking at that crease or fold in a particular way, then you may not be able to actually see a line there. And the line is only present if you can see it. Trying to get my scroll to work, and it's so epically not working. So the observation that we're making is that the contours are appearing as the surface turns away from the viewer. So, random objects off my desk again. This one's a baby toy. So this is a little rattle, and apparently my chroma keying is keying out the yellow. But as we turn away, as this round little buzzy bee, as the surface of its body turns away from you, that's where the contour appears. It's where the surface turns away from you. It's the edge of the surface as you're seeing it. And when you think about it this way, you realize that the angle of the viewer and the surface normal matters to the depiction of contours, because where the point where the surface turns away from the viewer, that's the point where the angle between the viewer and the surface normal is greater than or equal to 90 degrees. And that is an important observation to make, because we can take that and we can use that little fact in a shader to draw some contours. It's actually quite simple. So we're going to let V be the view vector. And just to remind you, the view vector is the vector that goes from your eye into the image. So that's the viewing vector. And it goes to the point of intersection. So there's our view vector. At the point of intersection, we have the surface normal, which we represent with the letter N. Now, whenever we're doing work with vectors that are direction vectors, we need to make sure that they have been normalized. And remember that normalized means that the length of the vector is 1. So if you were to compute the length by doing the Euclidean distance between the vector and the center point, which is 0, 0, 0, it would give you length 1. So normalization guarantees that. So you have to make sure you normalize these vectors before you do this, as we'll see. So then to figure out what the angle between N and V are, we can take the dot product of N and V, because that will give us the cosine of the angle. So if the dot product of n and v is 0, that actually means that the angle between the normal and the view vector is exactly 90 degrees. And if it's negative, it means it's greater than 90 degrees, so it's really facing away from us. And then anything that's if it's between 0 and 1, then it is going to be less than 90 degrees. So we could draw then a contour, i.e. draw black with our shader, anytime the dot product between the normal and the view vector is equal to 0. And that would give us a really, really thin line. Really, really thin. And the problem with comparison against 0 directly is that due to rounding errors on computers, you're going to end up, it's not going to be perfect. We generally want to use a threshold. So realistically, if you're implementing this, you want to do the dot product of the surface normal and the view vector is less than some threshold. And we will see that if you increase the threshold, that you actually increase the thickness of the contours that you're rendering. And it produces a pretty cool effect. So taking this simple observation and this very simple method, we can construct a shader very easily in Houdini. And I want to say, for those of you using Unity and for those of you using Blender or another tool, this is a very simple shader to construct. So the first thing I've got is I've got the incident vector. That's actually the view vector. And I've got the surface normal. And I've normalized both of them. And I negated the view vector so that the two vectors were like this instead of like this, because you want to make sure that they are pointing in the same way. You may not have to do this. It really depends on your tool. And then I take the dot product of the view vector and the normal. Now here's where things get interesting. The Houdini shaders do actually have the ability to do conditional logic, because I want to check, is the dot product of n and v less than my threshold? And I've set my threshold here to be 0.1. So you could technically use the conditional logic, the if block in Houdini shaders to do it, but you didn't really need to. And the reason for that is they have this comparison operator. So I've done a compare between the dot product and the threshold value, which is hard-coded here. It's not parameterized, but you could bind it to a parameter if you wished. And if this is true, that means that the angle is close to 90, which means we want to render it black. So this compare block will produce true. If, however, the angle is less than 90, it's going to produce false. Now, what's the interesting observation is that in most programming languages, true is 1 and false is 0. And I'm taking advantage of that particular fact to draw the contours. So you'll notice here that I create a vector with 3 copies of this comparison result. But before I just, stick, true or false into each of the X or R, G, and B components, you'll notice that I use the not operator, and that just flips it. So if it was true, it's now false, and if it's false, it's now true. That will make sure that the contours are rendered in black, and the not contoured area would be rendered in white, because 1 is white and 0 is black. And then I pipe that to the output color, and that's it. So, dot product, the comparison and against the threshold, and then this is where we use the inverse of the result so that the outlines are black. And again, that's where we're setting up the output color. And when we apply this shader to a lovely torus, you can see that we get outline. And you can see here that there's a little bit of shaded areas just in this kind of cusp in here, but actually it looks pretty cool, I think. Did a pretty decent job. So this was using a threshold of 0.1. And as I mentioned, if you want the contours to be a little bit more visible, then you want to increase the threshold. So if we increase the threshold here, you can see that it actually thickened the outlines a fair bit. And by thickening the outlines, what's really interesting is you can see that the outline actually doesn't have a uniform thickness, but it actually creates a pretty cool effect by not having that uniform thickness. And it has to do with how curved the object is. The more curvy it is, the faster than normal is going to be turning away from you, which means that you're going to get a different sized contour in that region. So it looks pretty cool. Now, torus is kind of a boring model to apply this to, so let's apply it to our good test friend, this dragon. And with a very, very tiny threshold, what you're seeing here is that contour is not really visible. A couple things going on here. This tends to work better on higher quality models. Number two, we need a bigger threshold. Oh, excuse me. So let's increase the threshold. When we increase the threshold, you can see that we are getting thicker contours and we're getting more details about the surfaces on the interior of the object, so you can start to see the scales. Now, one of the interesting things you'll note here is that the top of this is rendered in black, and that is actually because it is 90 degrees to the surface viewer, which means that it would get rendered in black. We can increase the threshold even still, and you get a really cool effect like this. And in fact, when I look at this particular one here, it actually reminds me a lot of what you would see in the comic book contours. I think it looks pretty realistic. Now, is this the only way that you can render contours using a shader? Absolutely not. In fact, there's another method that makes use of rear-facing polygons and culling to draw outlines as well. And if you take a look at some shaders that are done in Houdini and Blender, you'll see that they do use that other technique as well. But certainly doing something simple like the normals dot product with the view vector, really, really simple and pretty decent looking appearance. So now that we actually have the ability to render some contours using a very simple shader, we probably want to go back and talk about combining this with toon shading. So now you've got this problem if you've got two different shaders and you want to put them together. If you actually look in Houdini, let's open it up here, it's going to take a minute. They're actually separate shaders in Houdini. Let's open it up and let's drop I don't want to drop any fire. Let's drop a torus in here so you can see it. There we go. When we go to the material palette, these are all of the prefix shaders that you get. There are two non-photorealistic shaders from Houdini. There's the toon color and the toon outline shader. They are two separate shaders, and you can apply one or the other. So now I've applied the contour one, and when we render it, oops, because we don't have a light. We need a light. Here we go. Let's go over here and let's render. Oh, it's buggy. That's always fun. Unexpected. Either way, what you're seeing here, let's maybe make the outlines in red. I've never actually, I've used this shader the other day and it worked just fine. I don't know why it's not working today. Oh well, there you go. So you've got toon outlines, and toon shading itself is a completely separate node. And you can't combine them together. But ideally, we want to be able to produce something like the Lion King, where you've got the outlines and the toon shading. So how do you take these two shaders and combine them together? Well, there's lots of different ways that you could do it. Houdini has ways of doing layers. You can also make duplicate geometry and make certain parts visible. Or you can make a custom shader that combines the two together. And I thought that's what I would do, is show you how to take the two shaders that we've written in Houdini and put them together. It's actually quite simple. So this is our new shader. And at the top in this red block, this is actually our contour shader that we just built. And you'll note, however, that we don't pipe the output of our contours directly into the surface output color. And the reason is that we want to combine the contour result with the toon shading result. Down here in this other red box, we have a texture-based toon shader that actually uses a completely different technique than we showed you in the last lecture. As I mentioned, there are many, many different techniques for doing this, because really what you're doing with that texture ramp is you're just computing the UVs in some way to map into your texture map. So here I just used the results of the Lambertian shader. And I normalized that to give me the UVs. It's not a great result, but it's a result. It looks kind of cool. And then that's going to give me a color from the texture, and I want to combine it with the contours. Now, I know my contours are black. So if black is 0, which means if I multiply the output of the contour shader with the output of the toon shader, that anything that was black coming out of the contours will remain black when multiplied against the toon values. And anything that was white, which is 1, will keep its value. So I multiplied the output of the contour shader by the output of my toon shader, and that's going to give me this lovely result, which I think looks pretty cool. So you can see we've got the toon shading. And then we have the black outlines as well, and some of the creases and folds from the model are being highlighted here by the toon shader, but are also being highlighted by the contour shader as well. So that's one way that you can combine them. Now, things start to get interesting if you wanted to have colored outlines. Well, if you had colored outlines, then you would have to combine them in a different way. It's totally doable, but you just have to figure out which math operator you need in order to do that. Now let's change our toon shader up a little bit. So here's the dragon with a different texture for the texture ramping, and then with the black outlines. Looks very cartoony. Now one thing I want to put out there, so I want to go back to this shader. You'll see that I use this very almost random approach to getting the UV coordinates for the texture ramp for the toon shader. When you're dealing with non-photorealistic rendering, the goal is completely different from photorealistic rendering. With photorealistic rendering, I want to create the appearance of this toy exactly. I want you to see a photo of it and believe that it's the toy itself. Non-photorealistic rendering, you aren't trying to make it look realistic on purpose. You're trying to recreate a certain artistic style. It's about creating a particular look and feel. And what you'll see is that there's many ways that you can achieve that. And so I created this little texture ramp toon shader here with just 3 nodes. And you know, it's different from the one before, but it works. It gave me the look I was looking for. So something just to keep in the back of your head is that when you're dealing with non-photorealistic rendering, you can have fun and you can play around. It's more about do whatever it takes to achieve the look you have in mind than make sure this is super physically accurate such that it actually looks like a photograph. Creating art now, not photos. All right, so there's our fun one. Okay, that's nice. What if I want to do this for an image? Because that's something we have a tendency to forget, is we actually want to be able to take an actual photograph and apply these non-photorealistic styles to as well. So how would I do that to an image? Well, as we observed before, identifying contours or edges in an image is actually a very difficult task. In particular, one of the problems that we find is that edge detection algorithms or contour finding algorithms have really no way of differentiating between shadows and patterns and textures and actual object boundaries. So if you take a look at this photograph here, there are two cars in a building, and on the surface of the cars, there are a lot of reflections and shadows that create sharp lines. But these sharp lines are a product of the lighting and not actually a product of the surface. There is no crease or fold here. This is just purely reflections. If you look at the building, there's a placard above the door with the number 4 painted on it. And that is a flat pattern. It is not, if we were looking at the 3D geometry of this, it would just be a little square, flat square. The edge detection algorithm, and here I've actually used Sobel, can't differentiate between which lines we want are the actual contours of the objects and things that are lighting or textures on those objects. So you can see the harsh outline here of the reflection on the hood of this one car, along with the reflection on the hood of the second car. You can see the number 4 clearly. And you can also see outlines of shadows and other features that, again, these are not a part of the actual 3D geometry in the scene, and we don't necessarily want the lines for all of this. So the edge detection in image space really can't differentiate. An edge is an edge. It doesn't care what it belongs to. Now, just to review some of the other things, as another example here. This one is actually a little bit bigger. So this is actually a ray trace picture using my own personal ray tracer. And I think you guys have this model in the asset file, actually. And if you don't, I'll put it there. We have this cat, and it's a golden cat, and you can see there's a lot of reflections. And when we take the Sobel of this, we actually see this really strong edge here for the reflections. It's not an edge I want. And there's also a lot of noise. And that's one of the things we have to remember from before, is that when you're applying edge detection to images or contour finding to images, the noise in the image can actually have a really strong impact on the results that you get. And this noise comes from, these are JPEG images, which is a lossy form of compression. So it's compression artifacts. It can come from just noise in the camera, so i.e. like grain. It could be blur, because it's really hard to hold your hand still when you're taking a photo. Maybe that's just me. Regardless, there's lots of different ways that you get noise, and it creates this really noisy edge image with all of these edges, which technically, according to the mathematical operator that's being performed, they would be an edge, but they're not really an edge. And so if you want to clean up the results of these edge finding algorithms, you need to run a denoising filter on your photograph first. So in this case, I ran a medium filter with radius 3. Median filter tends to be my favorite go-to for denoising because it preserves the edges fairly well. Whereas if you remember when we apply Gaussian blur, it pretty much destroys the edges. Now there are other forms of denoising blurs that you can apply to preserve edges. The one that comes to my mind is the bilateral filter, which if memory serves me, does exist in the GIMP, but I don't think you have access to that in Photoshop. Although you can just create, a plugin, right? All right, so when we applied the median filter, you can see, and then we ran the edge finder again, you can see that the edges have been cleaned up a little bit. So in the pavement on the ground is a little less noisy, and there's a little less noise in a few other areas. It's a little bit cleaner, but this doesn't prevent it from identifying the fact that this reflection and shadow boundary are edges. They're technically edges, it's just not the edges we want. So here's the cat as well. This is before we applied a median filter to the cat. And then after we apply the median filter to the cat, you can see that it's cleaned up a fair bit. Although it wasn't that noisy to start with because it wasn't a real photo. It was rendered. Now, there's a number of problems that actually happen when you're doing this edge detection. And it's not, because I've used a really small median filter, it's not really present in these particular images, but it is something to be aware of. When you apply a denoising algorithm, especially something other than a bilateral or a median filter, or if you apply a really large bilateral or median filter, like the radius is really large, you're going to get bleeding of color. So it's going to, the red will bleed into the next area. And the problem with that is if you run the edge finder afterward, then instead of getting nice crisp edges, which are thin-ish lines, you'll actually get thicker lines. And they won't be sharp. They'll be soft, blurry lines. And that's generally an undesirable result. So be careful with your denoising filter before you run an edge finder, because you will not get crisp edges that you're expecting, at least for the edges that we've edge finding algorithms we've discussed so far. But now I'd like to talk about a different edge finding algorithm that isn't something simple. It's a bit more complicated. And it's called the Canny edge detector. Now, Canny edges are a bit more work from an implementation perspective. We'll go over the algorithm here in a moment. They are not typically a filter that you can find in things like Photoshop or GIMP, although certainly if you look online, you will actually be able to find plugins to add this ability. The Canny edges you're about to see, I actually did in Python using the OpenCV library. It's only a few lines of code. So the Canny edge detector, how does this work? Well, one of the things that Canny wants to do is it wants to try to figure out what edges are actual edges and what edges are just noise. So looking at this cat right here, I've got all these extra internal edges that were produced from the Sobel filter that aren't really edges, and we want to eliminate those. The other thing we want to do is when we're producing edges, we don't want them to be anything more than a 1 pixel wide line. So the Canny edge operator, what it tries to do is identify what edges are likely to be edges and thin them so that they are only 1 pixel wide. So how does it work? The first phase of the Canny edge detection algorithm is to apply a Gaussian blur to the image. And the purpose of this blur is to reduce the amount of noise, because we know that that's going to detract from our ability to identify edges. The other reason is that there are lots of edges that technically exist in your image, but they're so weak, barely visible, that we don't care to report them back to them in the image. We're calling these the non-essential edges. So when we apply the Gaussian blur to the image, we're reducing the noise and we're really trying to get rid of any of those non-essential edges. Because if you apply a blur and the blur gets rid of the edge and it wasn't a big blur, then that edge probably wasn't important to the image itself. Not always true, but sometimes true. Okay, so that's step 1. Step 2, we're going to identify where the edges are. And we find that by looking at the gradient of the image and where it is above some threshold. Now you might be thinking, what is a gradient in the image? Well, this is where we're taking the derivative of the image. We are looking for the change in the intensity of the pixel. So you can imagine, let's pick up this little remote here. As we go from right to left across this top here, we have all white pixels. And the change as we go from right to left in the pixels is none. So there's no edges here. But if I go down a few rows, and now I'm at where the buttons are, I have white, and then gray. And there is a harsh line between where it's white and where it becomes gray. So the change between that pixel and the gray pixel would be bigger. So as we're going across the image, we're looking at what is the change in the color from this pixel to the next pixel. And whenever that change is above some threshold, because there's always going to be some amount of change between the pixels, even in like a JPEG especially but there's always going to be some minute change. We're looking for that change to be greater than some thresholds. When the change is greater than the thresholds, then we say, you're an edge. Now, it's possible from that step that we end up with lines, edges that are thicker. And so when you end up with edges that are thicker, we're going to want to thin them out. So now that we have the thick edges, we're going to thin them out so that they're 1 pixel wide. And that will give us the nice thin edges that we are wanting in our final result. Now, after we've thinned them out, one of the problems that you're probably going to see is that some things that were edges are no longer edges. There's lots of noise left in the image. So then another threshold is going to be applied to remove much of the noise that was left over from the thinning stage. And now we have a whole bunch of edges, and we need to guess whether each of these edges is a real edge or something that might not be a contour that we actually want. So what we do is the Canny edge algorithm is going to look at each edge and look at the strength. Strong edges, that means it's a huge change in the image. We're going to keep those. But anything that's weak, that was identified but it wasn't as strong as some of the other edges, we're going to ask, is this a real edge or not? And the idea is that if a weak edge is connected to a strong edge like this, then it's probably an edge. But if a weak edge is just out there on its own, then it may not actually be an edge that we want to keep, and so it gets removed. Now, all of these different things, there's thresholds, blurs applied, there's many different parameters that you can manipulate with the Canny edge detector to affect what edges are going to get identified. And so when you're actually sitting down with an image, you're going to have to play around with those parameters in order to figure out what's the best way to get Canny to give you the edges you want. So let's actually see what this does. So here is our image from before. And then we are going to, this is just the Sobel operator. So this is not giving, Sobel operator after applying a median filter. We are getting a lot of noise and a lot of edges that we don't want. When we apply a Canny edge detector, this is the result we get. Now you can see here that it's still pretty noisy. We probably should have played with the parameters a little bit more, but I didn't for this particular image. If we had played with the parameters a little bit more, we could have gotten the underskirt here of the bottom of the bumper and remove some of this other noise here. But you'll notice that compared to this is really noisy. And the edges are thick and blurry, and there's lots of details that are being captured here that we don't want. And here's the Canny result. We've got 1 pixel wide black lines on a background. We have less noise and more actual edges being identified. So the Canny edge operator works significantly better than things like Sobel or Pruitt or the Roberts cross operators that you would find in something like Photoshop. And if we apply it to the cat, you'll see the same thing. So here's our ray traced cat. This is with the Sobel filter, and you can see there's lots of details we just don't want. And when I run the Canny edge detector, you can see that it gets rid of a good number of the details we didn't want and keeps many of the details we do want. All right. But there's something I would like to point out. Regardless of our edge finding algorithm, neither Canny or Sobel or Pruitt or Roberts cross, not Laplacian or different Gaussians or any of the different edge finding operators you find in GIMP or Photoshop is able to differentiate between shadows and reflections and actual contours of the object. This is the Sobel edge here for the reflection, or I guess it was the shadow, of the cat's head onto the cat's body. It is one of the strongest edges in this image. And even the Canny detector identifies it because it's a strong edge. It's a big change. And this is one of the fundamental difficulties when we're trying to do contour finding in an image. Without actually having the 3D geometry, it's very, very difficult to differentiate between patterns and light properties and the actual object itself. Are there any ways that we could actually improve this, though? How could we change it? Well, there's a few things that you could do. One of the possibilities is to actually identify the 3D geometry. So run another algorithm that takes your image and actually produces the 3D geometry for the scene. And then once you've got the 3D geometry, you can use any contour finding algorithm that you wish, because now you actually know the shape of the object. Now, of course, the problem with that is that the algorithms that are used to produce 3D geometry from a single photo don't work that well. And so getting that 3D geometry accurate enough to produce a set of contours, it's exceptionally difficult. Now, let's suppose you were actually dealing with stereo 3D images, though. This is where things get a little bit more interesting. If you have a stereo 3D image, then you can produce, or you might already have, a depth or a disparity map. And what's really interesting about the depth or disparity map is that it only contains information about the object's shape. It doesn't actually contain any information about the lighting or the patterns that might be painted onto the objects. It just contains information about the objects. And from that depth or disparity map, you could actually perform a 3D reconstruction, but you don't need to. So let's see what you can do. So here's the cat again, and I'm choosing the cat because I actually have a depth map for it, because it's ray traced. It's really easy to get a depth map if you're ray tracing it. And here is, this is actually the disparity map, which is, of course, inversely proportional to the depth map. So what you can see in here is there's no lighting. It's just a grayscale image where the color of gray, the intensity, reflects where this pixel could be found in the other image. And if we were to take the edges from the disparity map, because the disparity map only contains the surface, the actual object geometry, then this would give us the contours for the object itself. Now, it's not quite that simple. So what I actually found, because this is an algorithm that I worked on a couple years ago, is that if you try to compute the edges of a disparity map, you're not going to get all of them. And the reason is, if you look at where the floor plane meets the back wall, a human could look at that and know, oh, that's a floor and a wall. The computer can't tell. And similarly, where the body of the cat meets the plane on the floor, a human can easily see that that is two different objects. There's a boundary there. And unfortunately, if you were to apply an edge detection algorithm to that, it's really hard to identify uniquely. So the real trick to getting perfect edges from this, and we can do Canny, by the way, and Canny, it's not the Canny one. Oh, I didn't put the Canny one in here. Canny doesn't do a bad job, but it will miss some of them. So it will miss this floor plane and wall intersection, and it tends to miss where the cat's legs intersect with the floor. So it is, however, possible with a little bit of manipulations to extract a decent set of contours from this disparity map. And this is the contours that you can expect to extract. Now, the technique that was used to extract these contours was by partial 3D reconstruction. So what we do is we actually take the intensity of the pixel and we consider that the Z value. And then the XY position of the pixel will remain the XY position. So now that we've got a bunch of points, we use that to triangulate a mesh. And, well, we don't actually build the mesh. What we're actually doing is we compute the surface normals using the points. So you have a whole bunch of surface normals pointing out. And then we apply a shader to this that has red light coming from down the x-axis, green light coming down the y-axis, and blue light along the z-axis. And that unique set of lighting will end up turning this disparity map into a very uniquely colored image, where these edges that are where you have floors and walls meeting at funny angles, at least due to the camera, they suddenly become very visible, and as a result, then from that image we can actually extract the edges. Now, it's not a full 3D reconstruction. A full 3D reconstruction requires a lot more information than we have available to us. So we're just trying to use these points to create a pseudo mesh and to get the values, sort of. But the problem, of course, is that even though this does produce a really nice set of contours, this was the Canny. Not Canny, Canny. So ours were a lot better. You don't always have a disparity map. And if you don't have a disparity map, it's very difficult to produce one that is of sufficient quality in order to do this task. So the point I'm trying to make here is that image-based contour finding is an exceptionally difficult task that people have been trying to do for many decades, and we still do not have a firm answer for how to do this. So now we want to talk about how to shade our pen and ink drawings. So we've got our contours, and before, when we used toon shading, we had the ability to have, solid colored bands to represent the shadowed regions and the highlight regions and the midtones. But what if we wanted to show that shading by another technique, say hatching or cross-hatching, which are commonly seen in any pen and ink sketch, and also seen in things like pencil sketches? And as it turns out, we can definitely do this. And in fact, there are a great many different techniques that you could use in order to achieve the look. And in fact, these two images that are right here on this slide are actually from a paper from Hertzman and Zorin for adding these hatched lines to 3D models. So you can definitely do this with 3D models, and you can also create these hatched lines and cross-hatching in image space as well. So there's many, many techniques in order to achieve the look. So in particular, if we were to look at some of the technique from Hertzman and Zorin's paper, you can see here that they start out with the contours, and then they have this phase where they place the original lines. And if you look carefully at these lines here, what you'll see is that they're actually following what's known as the geodesic lines of the mesh. So they actually follow the contour, the levels of the actual model itself. And then there's a bit of a relaxation process, and then because of the different levels of shading, they selectively eliminate some to create these different looks here. So how exactly does their method work? Well, first off, we're going to look at it at a fairly high level. This is something, if you're interested to know more, I'm happy to point you towards the paper. The code was implemented probably directly. It was not implemented as a shader in something like Houdini. It's not to say you couldn't implement this as a shader in something like Houdini, because certainly many people have done similar things, but the code in this particular paper was not. So what they do is they're going to start by dividing the model into 4 different levels of brightness. And how they're able to do that, of course, is through looking at the lighting that is incident onto the surface of the model. So they might be using a Lambertian model of reflectance to compute what are the 4 different levels of brightness. After they've done that, they are going to draw the lines according to the vector field. And what the vector field is, it's a field of direction vectors that indicates what the direction of the surface curvature is. So, for example, if we had, let's pick a random object off my desk again. It's always one of those games of what is on my desk today. Let's choose my mouse. We have this mouse here, and if we were to draw, say, a vector field across it, we wouldn't draw it like this, coming up the mouse, because this is where the change is not happening at a great amount. We would draw it this way. The surface is changing in this direction. So they are going to start by choosing some points that are generally equidistant from each other, and they're going to create the hatches along the vector field like that. Hatches along the vector field. Hatches along the vector field. And then, of course, the cross hatches are going to be perpendicular to that vector field. So they're going to go up and down like this. And again, these would all be points that are equidistant from each other, because otherwise your hatches would have spacing that is, it doesn't make sense. Now, they're going to set the density of the hatches according to the brightness level. And so you would only see, so there's not going to be any hatching in the area that is brightest. In the area that is second brightest, you may only have sparse hatches. And if we look back at these diagrams here, you can see here how we have some hatches, but they're kind of spotty. And that's going to be your second level of brightness. And then the third level could be the crosshatched level, and then the fourth level would be the really dense crosshatching. And so that's how you're going to do this. So you're going to create all of them to start with, perform any kind of relaxations, and then once you've done that, to smooth them out and to make sure they're evenly spaced. And then once you've done all of that, you're going to selectively remove them such that you only are left with the ones that you want according to the brightness. And you get some pretty decent results out of this paper. And if we actually take a look at what's going on here, the hatches are being placed on what we call geodesic lines. Now, what a geodesic line is it's the shortest path between any 2 points on a curved surface. So if you've got this point here and a point over here, then this line would be the shortest path between it. You can actually see there's a whole bunch of paths between all of these lines. So these are the geodesic lines. And there is actually a tutorial for creating geodesic hatching for Houdini, and I'll make sure that you have access to that for this week's tutorial content. All right. So are there any other techniques that we could use to create the hatching for our shading? And as it turns out, there are many other techniques. One way that I've seen them before is to actually use a number of different textures. So you can actually create little texture files to represent each of the different brightness levels of hatching that you want to do. So maybe you want to have something really dense and cross-hatched for the darkest part of your scene, and then very sparse for the lighter parts. Create a bunch of different textures. And then what you're going to do is construct a shader where you first compute the illumination of the pixel. When you find the illumination of the pixel, you're going to either figure out which of the different brightness levels it lives in, and then create a set of UVs and choose a point from the texture to be your new color. Now, the interesting difference between doing this and doing the toon shading texture ramp is that with the toon shading texture ramp, we only ever had to worry about the U coordinate. We didn't need to worry about the V coordinate. Whereas when you're doing hatching, you're actually going to need to produce a V coordinate as well. And you might want to do something on the lines of what the actual position on the model, or something like that, because you're going to want to repeat these textures because they tend to be really small. So you're going to want to say, okay, well, maybe each full unit of the model's height will be the V coordinate or something like that. You've got to find a way to get a U and a V. And so you could do that, but that will tend to leave you with really harsh lines between the different brightness levels. So the other technique that you can do is to actually blend the different textures together near those illumination boundaries. And there are many tutorials in doing similar things to this, and we'll share them with you, of course, for your tutorial tomorrow. But these techniques do produce fairly decent appearances without too much effort. So what about images? Because obviously we don't want to just be able to stylize our 3D models. We actually want to be able to apply these techniques to an actual photograph. And we're going to actually see two methods for doing hatching and cross-hatching in the future lectures. As of this exact point in time, one of the techniques you're going to need to do this we don't have yet. And you will see that technique in the next lecture, and then we can talk about hatching from this other technique, which we'll describe in much greater detail in the next lecture. But just to give you a look ahead to the next lecture. We're going to tell you how to create this drawing right here. This is not human made. This is entirely done by a computer. Well, a photo was used as input, and then the computer algorithm produced this. But you can see here that we have these very messy hatched strokes throughout the darker regions, and in the next lecture we'll actually show you how to get these strokes. And you're probably thinking this is a really complicated idea. It's actually not, but it is pretty cool. All right. So now I'd like to spend a good amount of time talking about another algorithm called stippling. And many of you probably are familiar with stippling. It's where you draw something with very little tiny dots of ink or of paint. And the density of the points generally reflects the darkness or the shading of the region. So if you've got something that's really, really dark, I know the mouse is black, but the shadowed areas on the mouse would have a really high density of the stipples, whereas the highlight region may have no stipples at all. So stippling is an interesting way to create the shading. And there is a few simple observations that we have to make about stipple drawings. The stipples tend to be very evenly spaced, because the problem is when they're not evenly spaced, so if you get any clumping of the stipples, then it's almost as if the stipples are depicting some kind of feature. So for example, let's bring up a drawing tool. And I'm not going to be the world's best artist with a mouse, but if we've got a sphere and we start putting the stipples on, clicking them, if we suddenly do have a bunch of stipples that are really close together like this, and it might be totally random, but if you look at that little blip of stipples in amongst these other roughly evenly spaced stipples, we kind of start visually asking ourselves, is this a crack in the sphere? Or a piece of dirt on the sphere, or a pattern on the sphere? So when we're doing stippling, you have to be very careful to make sure that the stipples, while they are randomly placed, they have to be roughly equidistant from each other, because the second you have something that has a different density, it represents something else. It makes us think there's a feature on the surface. So you want to make sure that if there's no features there, that the spacing between the stipples actually is kept roughly the same. Now, obviously, the human hand is not perfect at doing this, but we are surprisingly good at it. And a computer can do much better. So let's think about some different techniques that we might be able to use to do stippling. One of the easiest things you might think of is, well, can't I just put a stipple could just be a pixel, and I'll just make it black. And I'll put a black pixel every k pixels. And the k will be really small if it's a dark region, and k will be bigger as the brightness of the area increases. So for really dark regions, we might have, a black pixel every other, like that. And then as we get brighter, maybe the black pixel will be every 2. So black to white, black to white, black to white. And then as we get brighter, black 3 white, black 3 white. Technically, that does work. But the problem with this particular technique that we've just mentioned is we actually get this unpleasant patterns appearing. And you can see it here. We've got these almost diagonals coming up from the bottom. That's not a desirable feature, because that makes us think that there's a pattern or a texture to the surface, when really we're just trying to convey the lighting or the shading. So this doesn't really look great. The problem is that we're not evenly spacing the pixels. Now, we could take into consideration the neighborhood. Say, okay, well, I've got a pixel here. I need to put one pixel roughly in this area. Where can I put it such that I'm not going to create these patterns? And certainly there are techniques to do that, and we'll talk about them actually a little later, because this is actually kind of the basis of a technique called dithering. But it's not really stippling. So I want to talk about an algorithm called weighted Voronoi stippling. And that probably sounds insanely complicated, but actually it's pretty neat and pretty fun to do. And this is an algorithm that was presented by Adrian Secord, I think it was in 2000. And what he does in this paper is he produces a stippled drawing using this construct known as a Voronoi diagram. And if you've never seen a Voronoi diagram, that's actually what I have over here on the right. And I know it's all bright colors and dots in random places, but it's going to make sense eventually. The idea behind this algorithm is actually quite simple. We're going to create some stipples, and we're representing our stipples during the algorithm as just points. We're going to distribute a bunch of random stipples across the image. Generally speaking, you want to put more stipples in darker regions than stipples in brighter regions, but it doesn't matter too much. And then what we're going to do is we're going to relax them. We're going to do this iterative process where we're going to move the stipple points until they're all equidistant from each other, or at least equidistant from each other with respect to the apparent brightness of that region. And the Voronoi diagram is how we're actually going to achieve this. Now, what is this magical, mystical Voronoi diagram that we have over here on the right? Well, if you look up any definition of this, it's a tessellation of a plane given a set of points. And the idea is that each of the little planes will contain exactly one point. So you want to splat down. You can actually make one over here pretty quick. So let's draw our box. Yeah, it's kind of a messy box. Let's put some, okay, that's 1 point. There's some points. And what we're doing to create the Voronoi diagram is we want to create a tessellation that makes it so that there's exactly one of these stipples in each region. Like so. All right, so this is our cool Voronoi diagram. Just a very simple way of tessellating a plane of points. And this is key to this algorithm actually working. So let's go back to our notes here. So this is the method that we're going to do. So we're going to create an initial set of points, and a lot of times you're going to, the implementation of this algorithm, you'll specify, oh, I want 1,000 points, or 2,000 points, or 20,000 points. And the idea is that it's going to take the image and it's going to randomly distribute those initial points across the image. Now, when I implemented this, I believe I placed more points in the darker regions than the light. So I kind of had like a distribution function that said, okay, if it's darker, then you get more points than areas that get lighter. This will make things a little bit easier later on for the algorithm, but again, it's not strictly necessary. Then what we're going to do is we're going to use the stipple points that we just randomly distributed across the image without care to what the image is, and we're going to create a Voronoi diagram from them. So now each point is actually going to lie in its own little region all by itself. Now, if we were to just leave things there, if you go back to this, you would note that these stipples, they're not evenly placed, even close. So obviously we're not done yet. And so what we need to do now is relax the system. And the idea is that we're going to compute what's known as the centroid of each of these regions. And there's various ways that you can do this, but effectively what we're trying to do is we're trying to find where's the actual middle of this region here. So we're not just looking for the middle along X and Y. It's like, what is the actual middle of this area? And what we do once we compute with the centroid, or the middle of each of these little regions, is we move the stipple point to the middle. What we are doing is we are forcing the stipples now to spread so that they are evenly spaced apart. Now, where does the weighted part come in? Well, obviously, if all of the stipples are exactly the same distance apart, then we're not going to get that distribution of stipple points where there's much denser stipple points in the darker regions and less dense stipples in lighter regions. So the weighted part is that we are going to apply a weighting to the computation of the center, such that in darker regions, the stipples will be much more attracted to each other, and in lighter regions, they will be spread apart a little bit further. After you've moved the centroid to the pixel to the centroid, or the weighted centroid, you're going to make a new Voronoi diagram. And you repeat this process until either no changes are made, which is unlikely, or the average size of the change between steps is beneath some threshold. Once you reach that threshold, you stop the process and you're left with your stipple drawing. So taking some images from the paper, this is what we have originally. So the thick black dots are the stipple points as they were placed, and the small black dots are the actual centroids of the region. So if this is our original tessellation of the plane, then what we're going to do for the first step is we're going to move each of these stipple points onto their centroids, and then we're going to do this process again and again and again. And if we keep doing it, this is the diagram that you end up getting. These stipple points are roughly randomly placed, but they're each equidistant from each other. It's pretty cool. And it does a really good job. This is a very, very fun algorithm to play with. So that sounds so simple, except for one big thing. How do you make this Voronoi diagram? And it sounds like it's a very complicated idea. It sounds like a big mathematical function you're going to have to do. And I'm sure if you look it up on Wikipedia or something else, it'll give you a long-winded algorithm and a bunch of math to tell you how to do it. Don't need it. There is a blissfully simple way to create a Voronoi diagram. And all you need is some cones. And I realize that probably sounds absolutely ridiculous, but it's also true. So what you're going to do to create the Voronoi diagram is to draw a bunch of cones. Now, all the cones have to be the same height and different colors. And they should all be the same radius. Now, you don't have to do the same radius thing if you want to do weighted Voronoi stippling. You could actually do different radiuses to account for the different spacings. But let's for now just assume they all have to be the same radius. So what you're going to do is for each of your stipple points, we're going to draw a cone such that the stipple point is the tip of the cone. So you might have to do a little math depending on how cones are specified in your tool to just shift it so the cone is below the stipple point. So just draw a field of cones in different colors. And then what you're going to do is you render it looking down at the cones using an orthographic projection. So remember, that's not using the perspective view frustum. That's just sending the rays straight through. And if you do that, and don't use any lighting, we don't want lighting, we want constant lighting, constant colored cones, you get a Voronoi diagram. It is that easy. And the reason why we want to render each cone in a different color is because we want to make sure that when we see our final diagram, that each of the regions is painted a different color, so we can then identify, oh, these pixels belong to this region, and these pixels belong to that region, because that's how we're going to compute the centroids later on. Very, very easy to do. So my own code to do this, I have not run in 14 years? No, it's not that old. It was 10 years. Either way, it doesn't actually show you the cones. So there is this wonderful website out there called GeoGebra, which I actually discovered because my daughter is using it to do Euclid's Elements. But they actually have a little app for creating Voronoi diagrams using the cone method. So you can go there, and I'll place a link on Brightspace so you can go and play with it. It's really neat. So now they've rendered each of the cones with lighting so that you can actually tell that this is indeed a cone. But this is, if we were to do the orthographic projection looking down, this is what you get. The black dots are the stipples, the tops of each of the cones, and then each of these colored regions represents one of the cones. And where the cones intersect, they create lines. It tessellates the plane with one dot per region. And if you don't believe me, these are cones. One of the neat things about GeoGebra is you can actually change the angle that you're looking at the cone field on. So I changed it so you're looking at the side, and that's what it looks like. So this is looking kind of like down like this. There's all the cones. It's pretty cool. So this big mathematical idea of this Voronoi diagram is actually incredibly easy to produce via computer graphics. Just draw a bunch of cones, and there you go, Voronoi diagram. And that's exactly how you implement this algorithm, is you would use OpenGL or whatever tool of your choice to draw the cones and then in different colors, and then you would compute the centroid of each region, move the stipple to the centroid, and then draw the cone field again, and just keep going and going and going until you make a minimal change. It's very easy to do. It's a very simple idea. So again, just to reiterate, we obviously want the darker regions to attract more stipples. And so you can actually weight things. And one of the ways that you can do it is in a darker region, you could make the radius of the cone smaller, so it's skinnier, which would place more cones in that area, and then use a weight in the computation of the centroid to make sure that it attracts them and they're much closer together. But there's another way that you can actually express different tones, and that is by altering the diameter of the stipples. Now, when we think of stipple drawings, we usually think of it's a pen point, and you're just all the stipples are the same size. But that's not explicitly a requirement. The stipples could change in diameter based on the brightness of the image. So we could actually alter the radius of the stipples according to the brightness. And that's very easy to do as well. After all we're doing is drawing circles. We can make them as big or small as we want. So just to show you some results, and these are actually results from my own code, my own implementation. This would be a gradient with black in the upper corner and white in the lower corner. And this is where all the stipples are the same size. And you can see that we have very black because the stipples are all tight together here. And then as we move towards the white, the stipples get further and further and further apart until we have none in the corner. So we get this gradient effect completely just with the spacing of these little stipple points. The other way of doing it was to do both, have that and also alter the diameter of the stipples. So this is the other approach. We've got much larger stipples, more tightly condensed, in the black corner. And then as we move towards white, you can see the stipples move further and further apart, but the radius or the diameter of the stipples is also decreasing as well. Personally, I actually like this result more than this one. I know this one here where the stipples are all the same size is a bit more true to a pen and ink drawing where you're stippling because it's the same pen, but I like this result a little bit more. That's one of the fun things about computer is, it's less effort for a human. So just some other results. This is this funny gear here, and if you're wondering why are there stipples missing along this edge here, there was a bug in my code. But it otherwise looks cool. So this was this was the stipples, and this is another one, and in this one I think all the stipples are actually the same size. So this is the image that was used as input, and this is the result we get. So they're cool drawings. Kind of boring though. So here's the truth. Now that you know how to place the stipples and spread them apart, you can now have fun with them. You don't have to render the stipples as circles. You could render the stipples as lines or hatches. You could render them as stars or shapes or any object you want. You could have a bunch of little grumpy cats or something. The other thing is that you don't have to render the stipples all in black. You could render them in different colors, colors according to the image, colors just for fun. It's a computer program, and you have all kinds of flexibility when you implement this method. It's very, very simple to make changes. So just to show you some of the possibilities from my own code. So this is the input image here, and this is our output here. And I've done two different things here. So one, I've used brown stipples and black stipples. So I have two different colors of stipples. And the other thing is that you'll note there is also some kind of contours or outlines in this particular image. And they're just short little lines. And actually, how those were rendered is quite simple. I produced the Sobel edges of this image here as a mask. And then I performed the weighted Voronoi stippling on that edge mask. But instead of rendering the stipples as dots, I rendered them as short lines, and the orientation of the line was dependent on the direction of the edge. There you go. So now you get this funky effect here. And I actually used that to create this really rough sketched version of these different buildings. So this one is this other church tower here. So again, same algorithm applied to a slightly different image, you can get some really cool results. Again, part of the fun of non-photorealistic rendering is the ability to just play with it. You're trying to create a cool visual result, which means you can just experiment with the parameters. Now, of course, you don't have to do black stipples on a white page. You could do white stipples on a black page. Or you could do purple stipples to get these cool grapes. I thought that was a fun drawing. And then this one here, I think I've had in the slides a few times. Again, this is just using two different colors of stipples. So you can use this algorithm and you can produce some really, really interesting drawings. Now, you might be like, can we have the code so we can play with it? I'm not sure the code will run because it's using libraries from a long time ago. But for the last assignment, you are in luck. There actually is an implementation of weighted Voronoi stippling. I have it. It runs in Windows. I haven't tested it on Apple yet, but it runs perfectly fine in Windows. And I will be giving you access to it. It's fully functioning. and it will let you do not just stipple drawings, but also a few other neat styles like TSP diagrams, that's traveling salesman problem diagrams, using the stipples. It makes this cool maze-like appearance. So that will be a part of your assignment 5, is actually using this tool to generate some interesting drawings. So that's really fun. All right, so now we have a way of doing stippled drawings. One of the downsides of this particular technique is it's not exactly fast. I want to say that on modern GPUs, if the code has been written in such a way to make use of the GPU's many cores, this should be reasonably fast. The program I'm going to be giving you access to, I don't think does that. So it is not the world's fastest program. 1,000 stipples will work very well, but if you tell it to do 1,000,000 stipples, don't be surprised if your computer takes the next 2 days to do it. Keep the number of stipples reasonable and keep the image size reasonable as well. Again, it's not the fastest algorithm. It's still fun to play. So what other techniques are out there for, creating shading other than actually just painting it in a color? Another approach, which actually predates stippling, is called dithering. And our original approach to stippling was actually a failed dithering algorithm. The idea behind dithering is when you are quantizing the number of colors, that's limiting how many colors you are allowed to have in the image, you are making it so that the shading in the image is no longer going to be smooth. And this could give you the toon effect, if you wanted. But if you wanted to have a more smooth reproduction of tone, and you've only got 4 colors to do it with, dithering is how we would do it. And the idea behind dithering is it's kind of propagating dots of one color into another to create the appearance of a smoother tone. Kind of like we were doing with stippling, except actual pixels this time, tiny, tiny, tiny dots. Now, we most often see dithering in a few places. You see dithering on printers anytime you are printing something, like a color picture or a black and white picture. Even though it may look like it's giving you a smooth tone, it's actually dithered. There is a pattern of yellow and a pattern of cyan and a pattern of magenta and a pattern of black dots that's put down onto the paper to give the appearance of certain colors and smooth tones. It's not, I mixed some of the blue ink with some of the yellow to give you this green tone. No, the printer does not mix the ink. It just lays the ink down in dots in particular patterns, which are very, very hard for the human eye to see unless you really get up close to it. So printing is definitely one of the places where you see dithering algorithms used a lot. Another one is GIFs. I know some of you are like, I don't like how you pronounce that word. I don't care. This. Pronounce it however you will. For me, it's GIFs. End of story. So GIFs generally have a restricted color palette, which means that they can't produce smooth tones. And so one of the ways that they create the smooth appearance of tone is through dithering. There are a lot of different dithering algorithms out there. Many, many, many of them. I want to talk about a very simple one. Excuse me. Called Floyd-Steinberg dithering. And this is a really common one. It's really simple. I'm not even going to show you all the math for it. It's fairly straightforward. The idea behind this is that you should be able to reproduce a smooth appearing tone using as little as 2 colors, so just black and white. You should be able to make it appear like a gradient. And so what you're going to do is you start in, let's just bring up a new page here. Let's discard that. Well, I'm not going to worry about that. So you're going to start in the upper left corner of the image. And you are going to, let's say we're just doing dithering with two colors, so black and white. So I want to choose how to quantize this pixel right here. And let's say I decide that this, and you choose based on which of the colors you're allowed to use is this current color closest to. So if this pixel was closest to white, then I would choose white. And if this is closer to black, then I would choose black. And let's say I choose black. Okay, so that's pixel is now black. Now the problem is this pixel wasn't actually black. Let's say it was like navy blue. And so there's some amount of error. And what we need to do is we want to spread the error out to the neighbors. So we're going to spread a portion of the error in that direction, and a portion in that direction, and a portion in that direction. So we're spreading the quantization error of the current pixel into future pixels that we have not yet quantized. And then we would move on to the next pixel to quantize. Except instead of this pixel being red, like it might have been originally, it's going to be red plus a portion of the error from the previous pixel. And so then we're going to have to quantize that. And then the error from that pixel will travel as well. So you're kind of pushing the error along. And the idea behind the Floyd-Steinberg algorithm is if you look at any region, the average error works out to be 0. So even though zoomed right in, there's definitely error that's happening, on average, the quantization error should work out to be 0. And the algorithm is very, very simple to implement. I have not put the pseudocode for that into your notes. If you'd like to see it, by all means, Wikipedia's pseudocode for it is I think it's like 10 lines. It's really simple. But as you can see yourself if you choose to. Now the results are very interesting. And again, they don't have to just be black and white. You can quantize to a fixed number of colors other than just black and white. So we have this picture of the two cars at the studio again. And if we dither that with two colors, this is the result that we get. And on average, the quantization error would work out to be roughly 0. And we see that, yes, it is small dots. You know, you can put your face right up to us and you see all the little dots. But at a distance, we see not only the details in the image, but a reproduction of the different tones as well. So there's a certain smoothness to the shading, even though it's completely done with black and white dots. And then, of course, we can do it in color. And this is, I am using black, white, red, and blue. Had to choose blue and red. And you can see here, like going back, so there's the original image. Black and white dithered, color dithered. You know, considering that there's only 4 colors in this image, it's a pretty good representation of that. You know, my first days of the internet, this was the norm. Websites often had heavily dithered images, and a lot of that had to do with the image formats not actually supporting a full color palette, but also that most people, when I first got on the internet, were still using dial-up. And if you wanted people to actually have your website load, your images actually had to be fairly small in size. And obviously, an image that is dithered is going to be significantly smaller than one that is not. So dithering was really popular back in the 90s. All right. So, are there any other techniques for shading and just creating interesting pen and ink like drawings? Actually, there's many. And if you go into stuff like tools like Photoshop or the GIMP, you're going to see a ton of different techniques available to you. And there are techniques that aren't in Photoshop in the GIMP, and we'll see some of those next week. Like, for example, that crazy rose, that's not in Photoshop, that's not in GIMP. They don't even come close to doing that. But I will show you the algorithm later. Okay. To be fair, they don't do it because the algorithm's mine, but there you go. Let's see some of the interesting techniques that are in Photoshop in the GIMP. So this is one. This is actually from Photoshop. And this is if you go into Photo Gallery and then Stylize, you'll find this one. And again, this has actually been rendered, the image has been rendered using just two colors, black and white. And if you look closely, it's a bunch of diagonal lines. It's supposed to kind of look like a pen and ink hatched drawing. And I mean, it kind of does. Now, how would they have done an algorithm like this? What they're doing here, well, there's a few techniques that they could have done. One, they could have done something very similar to weighted Voronoi stippling, but just using a large number of points and then rendering the stipples as diagonal lines. In here, they're all on a 45-degree angle, as you can see. Another approach that they might have taken is doing something like dithering, except using a dithering algorithm that instead of doing things on a pixel by pixel basis, does it on a block by block basis. So it might actually draw the lines. Or they could have just randomly, okay, here's a region. It has this level of brightness. What's the probability that there should be a line here based on the brightness? And if they roll the dice and it lands on one of their numbers, then it gets a line, and if it doesn't get a line. Many different techniques you could actually do to create this drawing here. And this is another one. This is half toning, and this is another printer technique, which many printers, it's kind of like dithering. It's very similar to dithering. The idea behind this is that you are reproducing, again, the tone of the image using usually just two colors. I think this one here actually has more than two. I think it is 3. But it tends to use larger blots. Dithering tends to be tiny pixels, whereas half-toning tends to be blots. And this tends to be more what you would see from a printer. And then this one here is stamp. Again, these are all available as the filter gallery from Photoshop. So they're very cool. And what you're seeing here is they've effectively thresholded the image. They said anything that is within a certain tolerance of black, painted black. Anything within a certain tolerance of white, painted white. And the results are very reasonable. Now, of course, the texture on the walls and the texture on the ground make things very noisy. And it ended up making it look like there's a person standing over here, except there really isn't. Like, it's a sign, but it ends up looking like a person, which is kind of funny. Now, some of the techniques that are not in Photoshop is the one that produced this other drawing right here. And again, we'll talk about how to do this particular technique in our next lecture. And I know it looks kind of wild and crazy, but it creates a certain human quality in its craziness. Whereas if you look at some of these techniques, it's kind of obvious that this was done by a computer. It lacks the human qualities of a drawing. It's too perfect, too precise, it's too rigid. Whereas this method here just produces crazy. And there's another example of it here. Same method, just a different drawing. All right. So those are all of the contour and shading algorithms that we're going to talk about today. In the next lecture, we are going to spend a lot of time talking about a technique called painterly rendering. And painterly rendering is giving an image or a scene the appearance as if it was paint it. So something, it's like wanting to turn your, let's go back to, I think we've got all the way back to the beginning. Let's turn this cat into, instead of, a golden cat that's precisely rendered, let's make it look like a Van Gogh painting. Okay. So that's the fun techniques that we're going to look at next class, is painterly rendering. And then we will also look at the technique to do that funny black and white sketch, which is a related algorithm. And then in the final lecture, because there's only 2 left, we will look at some other fun non-photorealistic rendering algorithms, including what I want to say is the state of the art, which is known as style transfer, which uses deep neural networks and convolutional neural networks to take the style of one image and apply it to another, which is a really fun technique. All right, so we will see you next week then.